Hi, this is Abhilash, and today we are going to solve a problem which was asked in Leetcode weekly context, the recent one. So it is 2059, so minimum operations to convert a number. So we are given a zero indexed integer array, nums containing distinct integers, and a corresponding start and a goal integer. There is an integer x that is initially set to start. Now you have to perform certain operations on this number x such that it is converted to the goal. Now we can perform the following operations repeated number of times. So the operations include addition, subtraction, and XOR. Now the range of the numbers of x is between 0 and 1000 for each I in the nums.length array. Now we have to note that we can use each nums_i any number of times in any order. So there is no rule about the order about which we take the numbers from the array. The operations that set x to be out of the range, that is out of the range from 0 to 1000, are valid, but no more operations can be done afterwards. Now we have to return the minimum number of operations needed to convert the start to the goal, and -1 if it is not possible. Now looking at this question, it appears that the most important constraint is the boundary between 0 to 1000. This indicates that we can apply any iterative mechanism to search for a particular number that matches our goal. Now the search will be basically a tree-based search. So in this case, we are going to start off with the starting number, and we are going to take all possible combinations, exhaustive search. The reason because this boundary condition or the constraint 0 to 1000 implies that we can use an exhaustive search in the time limit given to us. So that means for each array or each element in the array, we can add that element to the start, and we can subtract from it, and we can also do the XOR, and all possible combinations for each step will be generated. Now we can think of this as a kind of iterative search. So iterative search is best done with the help of breadth first search. So there may be a case where we want to solve this with recursion approach, and if we want to use recursion or memoized recursion DP kind of a thing, there is one disadvantage which I can think of in the fact that we want to return the minimum number of operations. Now for returning the minimum number of operations with the help of a DFS based DP, we need to actually know all the root to the leaf paths, among them which one has the minimum number of steps. All right, so this thing we cannot know beforehand. We can know this beforehand only with the help of BFS, because BFS tries to find the optimal path by searching through the neighbors rather than going through or towards the depth towards the terminal leaf nodes. So this may pass using a recursion or a DFS based strategy for some test cases, but I think for some other cases it may fail, because generally these types of questions, these are mostly suited for BFS. DFS, if we use that, then if suddenly we change the order of additions, subtractions, or XORing, we'll find that some of the test cases have failed, because it may have found some suboptimal paths or suboptimal search results rather than the optimal one. So this is our idea. So if you can think of a tree, so in this case, the tree is going to start from the starting number, so 6. All right, and we can branch off from 6, and we can take addition of 1 and 3. So 6 plus 1 or 6 plus 3. So we get 7 and 9 in the second step. In the next step, we can again branch off from the 7 and 9, and we can again do addition. We can do the XORing and the subtraction number of times. And we'll be finding that there are a number of intermediate steps which are overlapping. That means some of the nodes or internal nodes of the search tree is getting overlapped. So we have to remove those overlapping subtrees. So how can we do that? So just as we do in a normal BFS search strategy, we keep a temporary array, or I would say a vector or a map, which stores the visited indices or the visited values. So we can keep a similar kind of method over here so that we do not get the same value over and over again, so that the search is limited. Because if we do not keep that restriction, we do not keep a visited array for BFS, the nodes will get, again visited again. So even though if it is under a separate subtree, the nodes may get visited again. So that is the reason we are trying to have a visited subarray or an array present, which keeps a track of all the integers which are previously visited. Now, with that being said, we can see that the minimum number of operations required for converting 6 to the goal 4 is just xoring with 1, which is 7, and in the next step, xoring with 3, which we get 4. Now, this can also be done alternately. So 6 plus 1 is 7, 7 minus 3 is 4. So 2 operations in both of them. So in this case, the order of the operations is not important. We can have any kind of ordering for the operations. We have to return the minimum number of operations for this. Now, as we know, and we have seen that there can be multiple answers, multiple appropriate answers or correct answers for a given problem. And this is quite obvious because different search results can lead to different to the same solution in many cases. So if we think of the tree and if we think that a particular node has to be reached, there can be several paths which reach from the root node to the leaf node. In this case, the leaf node is 4 and the root node is 6. So if we go and try to implement this, since this is a competition, we're going to implement a minimized version of this. The main giveaway is that the x is bounded between 0 to 1000. So this is a very important point. In this case, that is the reason why we can apply BFS without any hurdles. All right. So in this case, let us try to initialize certain variables. The result is going to store my result. Since we are going to apply a BFS approach, we need a queue. Okay. Now we are going to push the starting element, that is our stepping stone, the starting element of the queue. Now, if you want to think of this as a tree, an array tree, then it can be our root node. All right. Now, the next step is to keep a visited vector. So in this case, I'm going to take a Boolean vector, let's say visited, and the bound of this visited is going to be 1000, let's say 1002, or for example 1001. So either ways, anyone will work because we are bounded by the number of the size of the array. That is the x, which is bounded from 0 to 1000. The next step is just pushing and iterating over the while not q.empty standard BFS loop. So what we want to do over here, first we want to take the size of the queue, because this is important. The size of the queue is important because for each size element, we have to take the topmost element from the queue, and we have to branch out all the remaining all the items that we're getting by adding the elements of the array from addition to subtracting and sorting, and then again pushing it back to the queue. And we have to increase the number of iterations. That means the answers, the result value, as and when we reach the goal, and we're going to return it. So for this, we have to keep s as let's say queue.size, for example. Now what we are going to do, we have to iterate over the size of the queue so that we keep a constraint on the total number of elements which is there inside the queue. Now for each step, it is important to increment the result. Why? Because for each, let's say one item gets popped out, and for that particular item, 3 subtrees are generated. Okay, 3 subnodes are generated, or 3, let's say, hidden nodes are generated. Now these nodes are just the addition, subtraction, and the XOR value. These are again pushed to the queue, provided they do not exist earlier in the queue. So for this, that counts as one iteration or one increase of the operations. So in this case, let us take the front element, which is the temp. Okay, now what we do, we have to pop that element. So we extract the top element of the, not the top, the front element of the queue. Okay. Now what we have to do in this, we have to perform certain checks. So what are these checks? The first check is whether the temp value equals to goal or not, whether it is goal or not. If it is goal, then it indicates that we have already reached our destination and we can return the result value. Okay, this is our answer. Now the second condition is checking whether temp is like belongs to a bound that is 0 to 1000, and also we have to check whether it is visited temp is true or not. So this indicates that if a subnode, that means an intermediate node, which is a non-leaf node, is already visited, we do not include it again in the queue. Okay, because it will just increase our runtime. So for this, we can just keep a temp like less than 0, or temp greater than 1000, or equals to greater than equals to 1001, or we can keep, let's say, a visited temp double equals to true. So this indicates that we are going to continue with this. All right. Now comes the third step. Now the third step is nothing but dequeuing. Since we already have the first element of, that means the front element of the queue in temp, we are going to mark visited temp as true. So visited temp equals to true, right? Now what comes next? We have to, since it's a BFS loop, we have to iterate over exhaustively over all elements of array. So for this, for auto I which belongs to num, let's say I want to keep 3 integers, let's say int I plus that means temp. So int b, it will going to be temp minus of I, and int c, it is going to be temp XOR of I. Now once this is done, the next step is just very simple. It is just pushing to the elements to the queue again. Now this is an exhaustive search with BFS. Only the difference is that we are not going like already visited nodes. We are not revisiting the already visited nodes. So this is checked by this condition, check number 2. Now once this is pushed, this loop will again go on expanding unless and until a terminal leaf node, which is the goal, has been reached. So once that is reached, we return the result, that is the final value. And until that, we increment the res, and also this indicates that no feasible solution is present. So in this case, since there is no feasible solution, we return it as -2. So ideally, this should be the approach to solve this problem. Now, let's see whether this is giving a proper result or not. So we are having this custom test case, which is already provided here. Let's see if we just try to run the code. So we can see that it is giving the correct answer. That means 1 and 3, 6 and 4, we already saw that there are 2 operations needed. For 2, 4 and 12, so we can add 2 to 12 to make it 14, and again 14 minus 2 is 12. So we have got the 12 in 2 steps. Similarly over here, since 3, 5 and 7, the starting point is 0 and the ending point is -4. So in this case also 2 steps are required. So in this case, we can add 0 plus 3, or 0 plus 3, which becomes 3, and 3 minus 7, which is -4. So against 2 steps. So similarly, the other conditions are also matched. This boundary condition, which is just a single element 1, 0, and 3, it is just returning 3 number of steps, because 1 plus 1 plus 1 at each step, since there is no other step required over there. So yes, so I think all the conditions are passing. Test cases are passing for this in the sample test case. So let's try to submit it and check whether it is right or wrong. So it gives an accepted solution. Now, I'm guessing that this should have a time complexity of around, let's say, time complexity will be of the order of O of n, because n being the number of elements in the array that we have over here, the nums array, but also into some constant. So the constant k is going to be the number of times the queue runs, or number of times the queue is non-empty. Okay. Now, how many times this can be in the worst case? So this k value is bounded by the restriction on x. Bounded by, let me just write it in this manner. So k will be bounded by restrictions on x, which is 0 to 1000. So within 0 to 1000, the k is again bounded. So we can think of the maximal runtime complexity for this is going to be somewhere around 1000 into n. We go of 1000 into n. Now this becomes quite trivial because n is always there for the internal for loop. For the outside, it depends upon the bound of x. Since that is how long the queue will be non-empty in the worst case. So this should give a feasible solution. If we were to try out with the DFS approach, just like I said, it may give correct results. But if we change the internal ordering, if we change, let's say, the order of plus, minus, and XOR, we get different results. And this is quite a common problem in other problems of Leetcode as well. So if we try to apply this logic in some grid-based problems, we'll be finding where DFS is more appropriate, we'll be finding that DFS approach, it does not give the optimal result. If we just change the ordering of this addition, subtraction, or XORing, we will be getting a different result, which is incorrect by the compiler. So this gives a proper solution for this particular problem. Very beautiful problem. Very tricky part is to consider this bound, which is x lies between 0 to 1000. Very tricky part. So in the next case, we'll be solving more such competition problems, which are really great, which may seem a little bit hard or difficult to solve at first, but it is just a simple operation of either graph-based traversals. So hope you like this video. If you like this video, please do subscribe to my channel. I will be posting more such content on this. And if you get another solution which is more innovative other than this, please feel free to post it in the comments and let me know.